let me introduce you to Mr. Pythagoras. You may have heard of him. He was a Greek philosopher. He taught religion and politics back around 500 BC. But he's probably best known for a mathematical discovery that he made that we are going to talk about today. So today you will need graph paper, pencil, or pen, and a ruler. So if you need to pause the video to get those things, do that now, please. All right, so what we need to do is, first thing, I want to draw some squares. And I would like you to draw a diagonal across the square, and then we're going to measure the diagonal. So to draw a square, you know that you have four sides of equal length. Let's see if I can do this here. Oop, that's a little square. I don't want one that little. I'm going to use my graph paper to hopefully draw an accurate square. So I've done 1, 2, 3, 4, 5, 6. This is a 6 by 6 square. Now, whatever unit of measure you use doesn't really matter, just as long as your sides are all equal length. So then you're going to draw a diagonal, and a diagonal will go from one corner of the square to the opposite corner. I made a big fat one here. So the question is, what's the length of that diagonal? Is it less than the sides of the square? Or is it greater than the sides of the square? Or is it equal to the sides of the square? A lot of times students think that it's going to be equal to the sides of the square, but I'm going to give you a moment. Can you measure that? And then let's see what you found. So was it greater than, less than, or equal to? Well, hopefully you found that it was greater than 6 centimeters or 6 inches or whatever unit of measure you used. Okay, so let's try with a rectangle then. Would the same thing happen? So we're going to draw a rectangle. And it doesn't matter which way you draw it, just as long as you have opposite sides that are parallel and congruent. They must be the same length. So now I'm going to draw a diagonal, if I can get my line here. I'll use something different this time. And again, whatever the longer side of your rectangle measured, would you expect the diagonal to be less than, equal to, or greater than that length? Well, what did you find? Hopefully, if you measure correctly, that diagonal length was longer than either side of your rectangle. So our friend Mr. Pythagoras named, his work had to do with right triangles. Now, what you just drew when you drew a square with a diagonal and a rectangle with the diagonal is that you split those figures into two right triangles. And if you recall, a right triangle is named because it has a right angle in it. So this right angle is where what we call the square corner. And in this case, you can see the right angle is here. And it happens where you have a 90-degree angle formed by the two sides of what was your square or what was your rectangle, okay? Now, when we have a right triangle, there are names for the sides. And the two sides that form the right angle are called the legs. And I don't know why he named it that, but that is what he named it. The third side of the triangle has a very strange name, and it is called the hypotenuse. And again, I don't know why, but what we learned by drawing squares and rectangles is that the hypotenuse should always be longer than either one of the legs. So that is what we're working on today, is understanding this relationship that exists between the legs and the hypotenuse. Now, you'll notice that there are some letters associated here. The legs are referred to sides A and B, and the hypotenuse is always going to be side C. Okay, that is just a given every single time. All right, so a lot of jokes made about Pythagoras. Okay, so this is what I'd like you to do. Again, using a ruler, I would like you to draw a right triangle. And this right triangle will have a height of 5 centimeters, I should say a leg of 5 centimeters and another leg of 12 centimeters. Now, it doesn't matter if you drew it this way or if you rotated it the other way, where the 12 centimeters was the height, as long as the two legs measured 5 and 12. Okay, and then I would like you to measure the length of the hypotenuse. Now, again, this is going to really depend on the accuracy of your measurements. But if you did this correctly, you should have gotten about a length of 13 centimeters. All right. Now, here's a right triangle where we have the hypotenuse and one leg, and we need to determine the length of the other leg. So you might want to start this one by drawing the 15 centimeter hypotenuse first, and then drawing a leg of 9 centimeters and then measuring the other one. So can you do that, please? Well, again, depending on how accurate your measurements are, you should have a B, another leg with a length of 12 centimeters. Now you might wonder, how does she know that? Well, there is a relationship that exists here. These are called Pythagorean triples. And the examples that we did, although we didn't do the first example here, but let's say when we had a leg of 5 and a leg of 12, this example right here, we found that the hypotenuse had a length of what? It was 13, correct? And when we had a length of 9 and a leg of 9 and a leg of 12, we had a hypotenuse of 15. So what about this first one, 3 and 4? Can you tell me what C would be? Well, the key is looking at these 3 columns here. So I want you to notice we had the 2 legs, A and B, and then we have the hypotenuse of C, okay? If you were to square each of the legs and add them together, you would get the length of the hypotenuse squared. So in the first example, 9 plus 16 is 25. The square root of C squared would give us C. The same thing here. If we added on the second example, 25 plus 144, you get 169, and the square root of 169 is 13. On the third example, 81 plus 144 gives you 225. The square root of 225 is 15. This is a relationship that Pythagoras discovered in all right triangles. So the Pythagorean Theorem, which is named after him, says that in any right triangle, and again, this is only applies to right triangles, the sum of the squares of the lengths of the legs is equal to the square of the length of the hypotenuse. And it's commonly referred to as a squared plus b squared equals c squared. So let's say we had this right triangle. Could we find the length of c squared without actually doing any measurement? Well, we know that if we square a and b and add them together, we should get c squared. So a squared would be 36. B squared would be 8 squared, which is 64, and that gives us 100. So if c squared equals 100, the square root of c squared is c, the square root of 100 is 10. So c would be equal to 10 centimeters. Now we have a side that's missing from this right triangle. So the important thing here is to make sure you know where, what the side is that you're looking for. So I'm going to rotate this image because I want to see that it is a right triangle, right? That this, what we're looking for, x here, is not the hypotenuse. No matter how it's positioned, I need to make sure that I understand this is a leg because it's part of the right angle. So if that's the case, we can still use the formula a squared plus b squared equals c squared. But now I just have to think about, I'm trying to find a squared. I know that b squared would be 6 times 6, which is 36, is equal to 9 squared of 81. And now I can subtract 36 from both sides. So a squared is going to be equal to 81 minus 36, which is 45. Now, 45 is not a perfect square. So now here's where we'll use our skills of simplifying radicals. We know that a then must be equal to the square root of 45. And we can simplify that by factoring out a perfect square of 9. So we can say a is equal to 3 because the square root of 9 is 3, and we're left with the square root of 5. Now, the thing about this is that you have to remember there's a unit of measure here. Our unit of measure is inches in this case. So we would say x is equal to 3 times the square root of 5 inches. Okay? I know that feels a little odd to have a radical as part of a measurement, but it is possible. Okay? All right, now sometimes the directions are going to tell you to round to a tenths place or something like that, but my preference will be that we show the result as a simplified radical. So it's not using a calculator, it is simplifying radicals, okay? So we have a right triangle, and so the first thing I'm gonna do is draw a right triangle. And the hypotenuse is 15 meters. And the length of a leg is 8 meters. What is the length of the other leg? So this is what we're trying to find. Okay, now it says to the nearest tenth, but I'm just going to show it as a simplified radical. Okay, so a squared would be 64, plus x is what we're trying to find. X squared is going to give us 15 squared, which is 225. So now we can isolate the x by subtracting 64 from both sides, and we end up with x squared is equal to 161. I don't believe that 161 has a perfect square factor, so I'm just going to leave it as the square root of 161, but I'm going to include the unit of measure, which is meters. Okay. So that is the Pythagorean Theorem. You have some practice to work on today, and then we'll do some more work with it later on this week. Okay? Have a great day, and I will talk to you soon.